Welcome to my channel. Today I'm going to discuss how to calculate Earth's umbra. The word umbra comes from Latin and it means shade or shadow. It's the root of the word umbrella, which gives us shade. An umbrageous tree is one that gives shade. However, in astronomy, the word umbra refers to the conical deep shadow that a solid body like Earth or the moon casts behind it. The umbra is the solid shadow where the entire source of light is blocked by the body. There is also an area behind the Earth and the moon where the sun is only partly blocked, lessening the total light received, but still allowing some light to reach it. This area is called the penumbra, and we are not going to be discussing that today. Why is the umbra conical in shape rather than cylindrical? The reason is that the sun is far bigger than the Earth, and when you go far enough beyond the Earth, away from the sun will extend beyond the edge of the blocking Earth, and it will pop out and be visible once more. When we calculate the length of the umbra, we are finding the most distant point where you could be sitting in a spacecraft and still have the sun completely blocked by the Earth. This point is the apex of the cone. This diagram is not drawn to scale, of course. A problem we have with trying to draw the solar system is the tremendous scale of things. The sun is 109 times as far across as the Earth. If we change the scale for both objects so that the sun is 1 meter across, the Earth would be less than a centimeter. This makes it difficult to have the sun small enough and the Earth large enough to see them both on the same diagram. Even worse is the distance between them. The sun is about 100 of its diameters from the Earth. So, not only are we looking at two objects that are very different in size, but using that scale, the distance between them would be around a football field. What I have done here is to shrink the sun and to expand the Earth while squashing the distance between them. It allows us to discuss the concepts and understand what is going on with the Earth's shadow, while still being able to see the important objects we are discussing on a single diagram. In earlier lectures, we have discussed calculating the distance between the Earth and the Sun. We have also discussed the values for the radius of the Sun and of the Earth. Today, we will use those values to help us find the length of Earth's umbra. We will once again rely on our old friend, the tangent function. The trigonometric functions allow us to calculate, given two values for a right triangle, such as two sides or one side and the value of an angle, the values for the rest of the triangle. Since we will be using triangles, let's put them in here. The hypotenuse of the large green triangle runs from the top edge of the sun through the point at the top edge of the Earth and on to the apex of the Earth's umbra. The other two sides of this right triangle include the vertical line segment running from the edge of the sun to its center, and another line segment running from the center of the sun directly through the center of the Earth and on to the apex of the umbra. The length of the vertical side is the same as the radius of the sun, labeled r sub s, and we know this value already. The horizontal line running through the object's center is partially known to us because the distance from the sun to the Earth is 1 astronomical unit, or 1 AU, the value of which we calculated in an earlier video. The rest of that line segment is the length of the umbra, L sub u. In other words, that side's length is 1 AU plus L sub u. The smaller blue triangle shares the same angle labeled with the Greek letter theta. Its vertical side is the length of Earth's radius, labeled r sub e, which we already know. Its horizontal side is the length of the umbra, labeled L sub u. As you can see, we have one side of both of these triangles, but not any of the other values for the length of sides or the size of the two acute angles. So, how can we use the tangent function to find out what we want to know? We are going to let algebra and geometry save us, because what we have are two similar triangles, which geometry has told us have the exact same interior angles, even though they have different side lengths. This means that the ratios between the side lengths for any two of the corresponding sides of either triangle will be the same. How will this help us? The tangent of the angle theta is found by dividing the length of the opposite side by the length of the adjacent side to the angle. That means for the big green triangle, we divide the radius of the sun, or r sub s, by the length of the horizontal side, which is 1AU plus L sub u. For the smaller blue triangle, we divide the radius of the Earth, or r sub e, by the length of the horizontal side, which is the length of the umbra, labeled L sub u. How does this help us? If we inspect the various items, we see that we know the values of r sub s, r sub e, and 1 astronomical unit. What we don't know is what the value of theta is, and therefore we don't know its tangent value. We also do not know the value of L sub u, since that is what we are trying to calculate. What saves us is the fact that the two terms for calculating the tangent value to the right of the tangent theta term are set equal to each other. In other words, we can simply drop off the tangent of theta from the left, and we are left with a single equation with only one unknown value, L sub u. Excellent. We can solve this and determine what the length of Earth's umbra is now. Our task is to get L sub u by itself on one side of the equation. By multiplying both sides of the equation by 1AU plus L sub u, and also by dividing both sides of the equation by r sub e, and then swapping the two sides of the equation with each other to get all the L sub u references on the left, we have this result. Now we can move forward to break out only L sub u from what is on the left side. We start by using the distributive property of multiplication over addition. If you look at the expression not as a division operation, but as 1 over L sub u times 1AU plus L sub u, you can then see how we can arrive at this new equation. And that will help us to simplify this even further, since L sub u divided by itself is 1. By subtracting 1 from both sides, we have L sub u only referenced once now. To get L sub u all alone, we multiply both sides of the equation by L sub u, and then we divide both sides of the equation by the expression r sub s divided by r sub e minus 1. Finally, we once again swap both sides to have L sub u standing alone on the left side. All the values on the right side of this equation are known to us, so our next step will be to plug them in. The distance to the sun varies throughout the year a bit, but the average distance is what we call 1 astronomical unit, and its value is 92,955,807 miles. The radius of the sun is 432,690 miles, and the average radius of the Earth is 3,958.8 miles. So now we'll punch these numbers into the equation and move forward. We'll start by dividing the two radiuses in the denominator. That is the ratio of the diameter of the Earth to the sun, and it tells us that rounding to the nearest tenth, you could stack 109.3 Earths from edge to edge across the face of the sun. Our next step is to subtract 1 from that ratio, and that leaves us only one more division to perform to get our final answer. And when we do it, we find that L sub u, the length of Earth's umbra, is 858,317.7 miles. It is interesting that that is very close to the length of the sun's diameter of 865,380 miles. And if you Google the length of Earth's umbra, it will say it is about 1.4 million kilometers. And as you can see, after converting miles to kilometers, you get 1.38 million kilometers, which nicely rounds to 1.4 million kilometers, and that acts as a double check of our work. In later videos, I will discuss how to calculate the diameter of Earth's umbra at various distances from our planet. If you enjoyed the video, please click like, and if you haven't subscribed yet, please do. Thank you for watching, and I'll see you next time.